Hello, I'm Peter Norton. Thanks for joining us again on ScheinTV. Tonight, our topic is hybrid ceramic materials. Now, if you're some kind of masochist and we're looking forward to an hour-long lecture on materials science, you might be disappointed. For the rest of you, you'll be very glad to know we'll be spending the next hour looking at real clinical cases that highlight the properties of some of these new hybrid materials. Our event this evening is scheduled to run for approximately 1 hour. As always, we encourage you to interact with us by sending us your questions and comments. In order to do that, please take out your smartphone right now, open the browser on your phone and go to Schein.tv. Once you've done that, click connect and you can send us as many questions as you like. We'll get to as many questions as time allows. By joining us here this evening, you're eligible to claim 1 hour of scientific CPD. At the end of the event, we'll give you instructions on how to register for your CPD certificate. But before we get started, let me tell you a bit about this evening's guest. Tom Bahahil is speaking on behalf of Vita North America and has been their technical advisor for over 12 years. As a second-generation dental technician, he was educated at the Technical Institute Anessens in Brussels and in his father's dental laboratory. As a fluent speaker of 4 languages, he often gives CAD/CAM and ceramic materials lectures, as well as hands-on courses across the northwest of Europe. He's also a guest lecturer at many universities and training centres. So, Tom, willkommen, bienvenue, welcome to ScheinTV.
Thank you, Peter.
Lewis Carroll wrote in Alice in Wonderland that we must begin at the beginning. So before we tumble down the rabbit hole of all these different materials, can you begin by explaining the theory behind hybrid ceramic materials?
Yes, the main component about a hybrid ceramic is a soluble feldspar ceramic. It's the same kind of ceramic a dental laboratory uses, just to layer metal or zirconia frameworks. But it's not a full 100% feldspar ceramic. It is actually combined with a polymer network. You have a main structure of like 84% feldspar ceramic and about 16% of polymer network. And these two networks actually, they intertwine completely, creating a hybrid ceramic.
And each of those networks is complete in itself, isn't it?
Yes, it is. But it is important that the ceramic part is the main component. The polymer is only the filler. You have to actually look at like concrete. Concrete itself is really strong. This entire building is made out of concrete. But concrete itself is also brittle. By the movement of the earth, by the people living inside the building, a building would not last long, it would collapse. We make buildings, we make concrete stronger, not by making the concrete harder, but by adding metal framework, a metal structure underneath. This gives the material much more elasticity, where it can actually cope with all those forces. So in order to make materials stronger, we don't make them more harder because they become more brittle, but we make them more elasticity, flexible.
Great.
So here you actually also see that if materials contain too much ceramic, they will become brittle, and the brittle material breaks, it chips, regardless of its flexural strength. So we try to add the same amount as flexibility like natural dentin, which is about 30 gigapascal.
Sounds good. So, and obviously that works very much in our favour for restoration, longevity in the mouth.
Yes, indeed.
Beautiful.
What you can also see here is that this material has main advantage. It can mill it extremely thin. Most people would think, well, the strength of the material is not so high. I mean, feldspatic ceramic is only 160 megapascal. So why should I use it then? It's because the strength of the material comes from its bonding. As you see in the statistics, that any kind of material that you bond becomes extremely strong, regardless of its final strength. But it's the flexibility of that material that allows materials to survive. Traditional ceramics are strong, but they're still brittle, which means you still need a minimal thickness. A simple shoulder or chamfer preparation. If you make these materials thinner, they will be more breakable. The advantage of hybrid ceramic is, even if you mill them razor thin, they still remain strong. The strength comes through its bonding, especially the bonding on enamel, and the flexibility will make it survive throughout the years. So here you actually see the difference between a hybrid ceramic and a traditional composite material. Because if I could say it's a ceramic combined with a polymer, then automatically you would think it is a composite. And a composite, you know the disadvantage and the advantage of composites. A composite wears off much quicker than traditional ceramic. A composite discolors throughout the years. A composite in general is a short-term solution. Well, and that's not what we want. We want a material that actually is a long-term solution, like a traditional ceramic, but not so brittle. What is a composite? Like say, a composite is a polymer-based material where the ceramic is the filler. A hybrid ceramic is a ceramic material where the polymer is the filler. It's actually completely the opposite. The easiest way to see the difference is whether you can etch it with hydrofluoric acid. In ceramic you can etch perfectly, 5% hydrofluoric acid, 60 seconds, where a composite, it does not work. There you have to sandblast in order to get a mechanical retention.
And if we were to etch a hybrid ceramic with hydrofluoric acid, would we expect the hydrofluoric acid to dissolve the polymer component or the porcelain or the ceramic component or a bit of both?
Yes. No, that's what the hydrofluoric acid does. It absorbs the ceramic part. That's why we absorb it for 60 seconds. But the polymer part will remain. So you had a good mechanical retention with the ceramic, and it will bond with the polymer inside of the material. So you actually get that perfect mechanical and chemical bonding strength.
Nice.
Where it's important to stretch that we can bond well onto it, that you can etch it. Because past experience showed that indirect composite restorations suffer massive debonding. In the beginning it allowed us to make partial restoration like inlays, onlays, and also full crown restorations. But quickly manufacturers realized that because of that lower bonding strength, because of that flexibility that would be too high at a certain point, it would lead to debonding. That's why we said we don't want to make a composite. We want to make a material that has the same properties like ceramic, meaning that it's a long-term solution, that it looks aesthetically like a ceramic, that it has the wear of a natural ceramic, that it doesn't discolor, and that it's good bonding properties. But I don't want my ceramic to be brittle, so that I can mill it razor thin. And that's the main difference between traditional composite restorations and a hybrid ceramic.
In the graph you showed earlier, it seemed as though it had similar flexural properties to dentine. Is that a deliberate development on behalf of Vita, or is it just a serendipitous event? I mean, is it because we're trying to bond mainly to dentine, or what's the reason?
No, it's actually a simple explanation. I mean, we try to reproduce nature. When we replace enamel, we're looking for a material with the same properties, with the same strength, with the same hardness, the same aesthetics. But if we replace both dentine and enamel, for example, well, we not only reproduce the properties of enamel, but we also try to reproduce the properties of dentine. So why make our material more harder or more flexible than dentine if we can just follow nature? So that's why we add 30 gigapascal. That's why we add 16% of polymer to the material. Not more, not less, which we could easily do. Here you see another graph easily to show the difference between composite materials and hybrid ceramics. In a composite you clearly see it's a polymer material, and you see the ceramic fillers in there. The more ceramic fillers, the higher quality it gets. A hybrid ceramics, you clearly see it's not really a filler, two networks, two structures that actually intertwine. If I show you what happens when you etch this type of materials, you actually understand it better. A polymer material, a composite material, cannot be etched. You can't get a decent retention on it. So that's why we have to sandblast the restoration. Where in a hybrid ceramic, you can see on the graph, it etches nicely. The polymer network now is quite visible, and that's where it actually bonds onto. It's also important to stress again that we want a material that lasts for a long time. We know, here you also see it if you do the toothbrush test, the patient will brush his teeth hopefully every single day, well, these types of material, this composite material, starts wearing off much quicker than traditional ceramics, and we don't want that. But it's because they are much softer.
And for the sake of our viewers, the German translation at the top of those graphs relates to loss of material from the material itself during toothbrush testing. Is that correct?
Yeah, it actually shows us how much material will wear off in total and how much would wear off in depth. These numbers don't need to be precise. What's important to understand is that a composite is notorious for wearing. It wears off rather quickly, where a normal ceramic has a more antagonist-friendly type of material, is a material that lasts much longer, it does not wear. People would think, oh, it contains polymer, so it's like a composite. It will wear off dramatically, and that's not it. It behaves like a ceramic. A hybrid ceramic takes the advantage of a traditional ceramic and the advantage of a composite, but none of the disadvantages. It's the best of both worlds.
And you mentioned wear on the antagonist or the opposing teeth. So from what you're saying, it's much kinder to the opposing dentition than a traditional ceramic. Is that correct?
Yeah, of course, a lot depends on how you actually polish the final surface. I mean, a harder material in general wears off more of the antagonist. A softer material would be more antagonist friendly. If you would polish a material really, really smooth, even the hardest material can be very antagonist friendly. Even zirconium dioxide can be extremely antagonist friendly as long as you polish it well. But the harder material is, the more difficult it is to polish. And we don't have much time in our practice. We need to work as quick as possible. So what we want to do is, we want a material that's antagonist friendly, quick and easy to polish. And that's why we chose a hybrid ceramic.
Beautiful.
So if you're asking me now, let's say, well, but Tom, where do we use enamel? Then what's the ideal indication of using enamel? Oh, actually, skip this. Where we actually use enamel, then it's this type of patients. It's patients with worn dentition. We see them more and more. I mean, yes, the manufacturer will tell you enamel is great to do an inlay or an onlay, but it has a much better goal and much better properties. This type of patient that you see here in the picture, patients with worn dentition, it could be a heavy grinder like myself, it could be to acid reflux, it can be any reason that worn dentition needs to be replaced. This type of minimal invasive dentistry, non-prep preparations are difficult to deal with ceramics because you see the patient has healthy teeth. I mean, you're not gonna prep anything. A dentist doesn't want to prep in this case. The enamel that we have, we want to keep to bond onto because you know that the bonding on enamel is much, much better than bonding on dentin. The more I prep, the lower my bonding strength. And I need my bonding strength in order for materials to survive.
So if in that case there, if that's going to be performed as a minimal prep case, obviously that the material, the hybrid ceramic material is going to have to be milled incredibly thin at certain areas. Is that something that these materials can withstand?
And that's the beauty of this material. Again, where a traditional ceramic, regardless of its final strength, regardless you take a feldspar of 160 megapascal or a lithium disilicate of 360 megapascal, they are brittle, they need that perfect shoulder chamfer prep. That needs 1.5 millimeters. That's massive. If you prep that much, your enamel is gone. And you need again that enamel to bond onto if you want your materials to survive. Another reason why we don't want to prep is because the more we prep, the more we weaken the tooth structure. In this case, the wear is limited. The tooth structure itself is quite strong. But you will see a next case where those walls become extremely thin. And if you then would put on a ceramic or even worse, a zirconia restorations that doesn't absorb any of your forces, you might not break the restoration. The restoration will be safe, but maybe you break the tooth structure itself, and then we're in much bigger problems. So these type of patients we actually want to treat non-prep for the sake of patients, conservative prepping, for our bonding. So that's the problem that many laboratories face nowadays, is that the dentist has a case like this. He asks the laboratory, how are we going to solve this? And the lab says, well, if you do a prep, a nice shoulder chamfer prep, I'll give you a ceramic. And the dentist says, well, I'm not going to prep. And the lab says, well, sorry, I don't have the materials to help you. And what's your last choice? Direct composite restorations. That works well, but that's a lot of work.
Yes.
We don't talk about a single restoration to repair. We talk mostly complete occlusal rehabilitation instantly, like 10 to 20 units. Unless you have only one patient a day, you can't put in so much time. And again, a composite is only a short-term solution. That's not what we want to have. So you want to treat these patients where you as a dentist are not going to prep, you're just going to take an impression and we're only going to replace what's been lost. I can show you an easier case here. Same thing, patient has worn dentition, we can prep everything and we can make full zirconia crowns on top. But why should I lose healthy tooth structure? So what we're going to do is, we don't prep anything and we're just going to replace what's lost, like here. And this is important because sometimes these outlines will become razor thin. Sometimes you have to go almost to zero. And again, a ceramic cannot handle that. But because of the flexibility of a hybrid ceramic, it can. You can mill these things razor thin. To give you an idea, officially, you can mill anemic for veneers to 0.2 millimeters.
Wow.
0.2 millimeters is paper thin. If you don't be careful, you actually already break them during polishing. So this is a kind of veneer that you bond in first and then polish. But it allows us to make real thin preparation or just non-prep preparations. Of course, people would think, well, if it's that thin, it's going to break. It's going to break instantly. No, because when you prep that thin, there is so much enamel you can bond onto that the strength goes through the roof. A very thin anemic restoration from only 160 megapascal bonded on enamel will be in the end stronger than your lithium disilicate restoration of 360 megapascal. Strength comes through the bonding, the flexibility makes it survive. Only when your bonding is terrible because you prepped so much, because you can't keep it dry, because you don't follow bonding protocol as it should, only then flexural strength becomes an issue, because then it's the material that needs to be strong. But often that means that you sacrifice other advantages like aesthetics, precision, ease of use, etc., etc. And that's the great thing. These type of patients, minimal invasive dentistry, this is how we treat it. An indirect way, so you as a dentist only take a traditional impression and send the work to the laboratory, but that you can do it in a modern way, a non-prep way.
So in a case like that, if we were to expect heaven forbid, a failure, would we expect a failure within the enamic material itself or at the bonding interface, if protocols have been followed correctly?
If protocol is followed correctly, that means you have enough enamel to bond onto, and I'll show you some cases later on where you can actually see how much enamel you're going to need. If you follow bonding protocol correctly, it's never the bonding that fails. You have to understand that every material can break. If you put enough load on zirconia, even 1200 megapascal breaks. If you have a decent bonding protocol and a correct occlusion, because this is what, in this case, we're not replacing a single crown, we are building up occlusion again. If you make sure that you have a decent canine guidance, that your occlusal forces are well positioned, then don't worry that it's going to break. It can handle those forces due to its flexibility. But imagine something goes wrong, because you never know. Patients have an accident. In Belgium, patients open beer bottles with their teeth. And then they say, no doctor, nothing went wrong. This has just happened overnight. Then as a dentist, you can repair your restorations. You can just roughen it up with some diamond burr. Use a silane, like a popular silane like Limebonon Plus, for example, and some direct composite. You can repair what's been lost. You can even do root canal treatment after you bond it in the restorations. You can actually drill through the restoration, do the root canal treatment without damaging the restoration and seal it back afterwards. That's how much abuse it actually can take.
And is that because of the crack stop mechanism that's built into the polymer, or that's afforded by the polymer?
Partially. On the one side, of course, it's the flexibility, meaning if you have a material, it absorbs actually force. You need a lot more force before you can crack. It's actually funny that we always look at this 1200 megapascal, 420 megapascal. That's so important for us if the natural tooth only has 100 megapascal. Often you see cracks in the enamel. You take a light and look at the tooth, you see cracks in the real enamel. So why doesn't the tooth structure break completely then? Because underneath there is a dentin, a flexible dentin that actually absorbs all the energy, and the crack goes all the way to the polymer, to the dentin, and stops. And here's the same thing. Because of the flexibility, you need a lot more force before it can break, before it can make a micro crack, and the micro crack will build in the ceramic maybe. It can't continue in the polymer because the polymer absorbs that crack, like real dentures do.
If you've just joined us and want to submit a question, take out your smartphone, and on your smartphone open your browser and go to Schein.tv. Click connect and you can send us your questions that way.
I have another interesting case to show you where it follows the same procedure, where we treat our patients in a minimal invasive, non-prep way. If you would be concerned, for example, about the aesthetics, then don't be. I mean, I know that the material that contains polymer, you have the impression that it always doesn't look so nice as a traditional ceramic, but it's because you use it actually in the wrong indication then. A ceramic will be nice even if you make it really, really thick. But here is the opposite. We try to make it as thin as possible. And the thinner you make it, the nicer it will look, even if it contains a polymer. You can see if I finish this case, some of these restorations are extremely thin. And the thinner you make them, the nicer it gets.
Why is that?
Well, because it contains less polymer then. That's the thing. If you look at the block before it mills, everybody would think, oh, that's really opaque. I'm not going to use it. Ceramic is much nicer. But again, we're not going to prep 2 millimeters because yes, then it looks more opaque. But that's not what I want, because my enamel is gone. Then I have enough room to do a traditional ceramic. But mill them thinner and thinner, they become nicer and nicer. And again, strength comes to its bonding and the flexibility makes it survive. And you see in this case, it's all done in a hybrid ceramic, a polymer containing material, and it looks as nice as a ceramic.
It does.
So I'll give you another case. This is a case we done together in Holland with the University of Amsterdam. And the same thing, patient walks in, she's like 34 years old, anorexic. We solved the anorexic, that's not a problem anymore, but she has some heavy worn dentition due to the massive reflux. When we look at it first, we thought, oh, it's okay, it's not so much, we can fix this with some direct composites, no need as a lab to interfere. But when we looked a bit more into detail, you see that it's massive. We can't solve this with direct composite. It would take you ages to do so.
You'd also be worried about sort of developing an effective occlusal scheme, I suppose, as well, in a way.
I'm glad that you say that.
You can't in a lab.
This is not just simple rebuilding one simple inlay or a crown. It's rebuilding complete occlusion. Doing this in a lab, in wax, in articulator is already a lot of work. Imagine you have to do this in the mouth with a patient who's sitting there for hours and hours. This is not going to be fun. So that's why we say let's do it in an indirect way, since direct is a bit too time consuming. Then you can say, okay, we can do everything in zirconia. Zirconia will never break, so we're safe. But look how thin those walls are getting. I mean, zirconia doesn't cope with any energy. All the energy will go into the tooth structure underneath. And maybe restoration won't fail, but your tooth might break. And then we're in much bigger problems. So zirconia is already out of the picture. You can say, oh, let's do a traditional ceramic, like we've done so many times before. We can, but then we have to start prepping. And we told, we need that enamel. You see that thin ring of enamel?
She's already lost a lot.
Yeah. But that ring of enamel is enough to bond onto. So we just say, okay, we can clean it up a little bit, but furthermore, we're not going to touch her. We want to keep the strength of the remaining dentition, and we want that enamel to bond onto. So we want to be minimal invasive. We want to be non-prep. So all our traditional ceramics are laid on site. We can do an indirect composite restoration. There are many options, many brands to choose from, but we know from the past, because of the difficulty, you can't etch it, the lower bonding strength, that these materials suffer heavily debonding. So what's left to use? I want a material that I can mill razor thin in a non-prep way, but on the other side, like a ceramic that I can bond, that looks great, like a ceramic, and that doesn't wear or discuss. I don't see any other option here than using a hybrid ceramic. And as a dentist, it's fun, because see, these are all the units that we had to replace. This is a lot of work, but we didn't prep anything. What we actually did is, as a dentist, you just took a normal or digital impression and you send it to the lab. The lab will design everything, the complete occlusion. As a dentist, if you say, yeah, but I want to be in control of that occlusion, I want to see it for myself, then we can still do that, because we can put you on a team viewer, you can sit next to me when we design it together, and you as a dentist are still in control of the incomplete occlusion. You can follow traditional occlusion, or like in this case, the dial principle, where we put most of the forces on the interiors. But you're still in control, even if you give it to a lab indirect. In the first meeting, the first session with your patient, you don't do much. You just explain the situation, you clean up the situation, and you take an impression. It's only in the second step, when all the restorations are made, that you as a dentist start working. Because now it's your time to start bonding. And here you see, in this case we used Panavia aesthetic cement, 5% hydrofluoric acid for 60 seconds, and that's important, 60 seconds. To give you an idea, glass ceramic is only 20 seconds. So, you see.
So we've had a question. Can we over etch the the enamic material? If we etch for longer than 60 seconds, would it weaken the material?
Yes, it's not so sensitive as a glass ceramic. Glass ceramics are a bit more notorious for over etching. There it's important that you only etch for 20 seconds. But not only because you would weaken the material, but also that this calcification you see after bonding, white spots everywhere, it's just not nice. Where a feldspar ceramic or a hybrid ceramic you etch for 60 seconds. But if you would over etch, yes, you would weaken the material, and that of course leads to more risk to fracture.
And another question, which is probably just revisiting what you've already said, but just for emphasis, it seems that enamic can be made very thin for the occlusal surface. Are you concerned with it being so thin that it could fracture? Because we're told usually at least 2 millimeters, but the cases you've shown are a lot less than that.
Yeah, you have to understand it's not easy for me. On the one side I'm a dental technician, on the other side I represent the manufacturer. The manufacturer will say that instead of milling 1.5 millimeters, we can go occlusally to 0.8, which already have. But of course, you've seen cases that I show where actually even went thinner. From my experience, you can go thinner, because again, the thinner I go, the more enamel I keep. The more enamel I keep, the stronger they get. I'll give you a personal approach. I'm a grinder myself. I've heavily worn dentition. I'm not going to smile in front of the camera, but take my word for it, everything is worn down. I've tried to rebuild my occlusion like 5-6 years ago, before we had hybrid ceramics. And the only thing I had was a pressable, weak feldspar ceramic. It was brittle, but at least it was a nice material, and I could press it razor thin. So I'd go for it. They were pressed like 0.5 thin. I still have all of them. Imagine that I would say to you as a dentist, we're going to treat a heavy grinder, non-prep, with 0.5 weak ceramic restoration. You think I'm crazy. But it was the best. I have a laboratory at home, so I can take the risk. If they break, I make myself new ones.
That is handy.
I have them for over 5 years, and they're all there. Why? because even though they're razor thin, I've bonded it on pure enamel. And it's the bonding that gave me the strength. But what happened is because they're not flexible, they don't survive over a long year. They don't break in 1,000 pieces, but they will, the unsupported parts will chip away. That's why I need flexibility. That's why I have to go now to Holland, drive 200 kilometers to find a dentist that will take all of them out and replace them in a hybrid ceramic.
That was my next question. If and when they fail, will you consider a hybrid ceramic? And you've just said
I
yes.
have to. I see for me no other option. I have healthy dentition. I'm not going to prep anything, but I do need to build up my occlusion. So I don't see any other option than a hybrid ceramic. I know that my traditional feldspar ceramic has helped me until now. Like I said, the wear is excellent, the aesthetics is excellent. Due to the bonding on enamel, it's really strong. The only thing I was missing was a flexibility to avoid the chipping, and that's what a hybrid ceramic delivers. So I'm actually really happy, not only as a dental technician to work with it, but also as a patient myself. So yeah, I'm actually looking forward. Well, not looking forward, but I need a solution.
Well, you have some more photos for your PowerPoint. That sounds great.
That's actually what I'm doing. I'll actually show you how we finished the case here. Here you actually see we etched it with hydrofluoric acid 5%. You clearly see the good retention we're having with the polymer. Silane, 60 seconds, and just complete the bonding. And the only thing as a dentist what you actually do is after putting the rubber dam is just fit them one by one, just to make sure that there are not any contact points that are wrong, if there is any problem with the occlusion, and then just start bonding. One by one you start bonding them. And what you see here is a patient that didn't like it anymore after 3 hours. The patient was lying with their mouth up for 3 hours, people were taking pictures and so on. She said, no, let me go home, I'm sick of it. And we said, okay, that's not a problem. You can go. She was already happy, by the way, because she came in with nothing and she walked out 3 hours later with a complete rehabilitated occlusion.
Absolutely.
She was jumping. We were not happy because it was not finished yet, but we said, go home. Because you have to get used to a new occlusion. It takes some time. The higher you raise it, the more time it takes. It took me about 4 days in my time, in my restoration, to get used to it. They say that a softer material, you get used to a lot quicker. I'm really hoping so. And we said to the patient, come back next week. Here you also see the pictures. This is how the patient went out. I mean, we didn't like it much. I mean, in a functional way, it was a dream.
Yes.
The occlusion was rehabilitated, you got canine guidance again, but on aesthetic approach, it's like, really? But then the patient was, no, I go home, I love it. I'll come back next week.
And what was the plan after that stage?
Well, our plan originally, here you see when the patient came back, the dentist took it with the right front, it's a bit blurry now, but our approach was, well, let's take some nice veneers. Let's do some nice ceramic veneers. Let's do a minimal prep, and in a, not a hybrid ceramic, but in a glass ceramic, let's take some nice veneers with that ceramic opalescent effect. Must be awesome. And the good thing is that you can prep within anemic and make it part of your preparation. You can bond onto anemic perfectly. But we didn't go through because we had a financial problem. I mean, you're talking about the 34-year-old patient. She's not a millionaire. We already restored 20 units. So we said, let's just clean it up with composites, because again, anemic is repairable. We can just roughen it up, the structure. Use a silane like a monobond plus with some direct composite repair it, and just monitor. Patient has to come back anyway to check if there still is canine guidance after 6 months, and that's a good thing. If material starts wearing a bit too much, then you can repair it. And that's what we did here. Patient came in, and the last session is that he just repaired everything with a direct composite.
And that answers a question that just came in. Can I use composite to make small adjustments?
Yes, perfectly. Of course, only small adjustments, because the more you replace the anemic by a direct composite, the more you change your properties from a long-term solution to a short-term solution.
Understood.
So, but it actually works perfectly.
We also have a question. How is anemic different from other hybrids on the market?
Well, that is actually a tricky question because, well, a hybrid ceramic officially does not exist. A hybrid.
As in, other hybrid, so competitors don't have hybrid ceramics?
Everybody can call this material a hybrid ceramic because it is actually not a scientific name. Why did we call our material a hybrid ceramic? Because again, if we say polymer ceramic combination, everybody thinks, oh, it's a composite, which we know since the 70s, and we know its advantages and disadvantages. We wanted to make sure that people understood that we don't make a composite. We make a ceramic material with a polymer filler. So we gave it a different name, a hybrid ceramic. And now there's so many different brands on the market that try to make polymer ceramic combinations. You have GC Cerasmart, you have the Chauve, Voodoo Colt and Weldon, and the original block from 3MS Lava Ultimate. These were composite blocks, polymer materials with ceramic fillers. Okay. True, it's a highly ceramic filled material, but the core material remains a polymer. How can you tell the difference? Try to etch them. You will see instantly the difference. So why didn't this manufacturer call it a composite? And why did you desperately wanted to call it a hybrid ceramic? Because of the negative feedback we had with Lava Ultimate back then. Lava Ultimate was indicated for inlays, onlays, veneers, and full crowns. And after like 2 years, they took that indication from full crowns back because of the massive debonding they had. So every manufacturer said, don't call it a composite, because people will think that we will start debonding. Let's call it a hybrid ceramic, because that's popular now. So everybody may call their product a hybrid ceramic, but instead they're only indirect composite. There's only one true hybrid ceramic. That's a Vitadynamic, since it's the only material, is a ceramic block with a polymer filler that can be etched. All the other ones are polymer blocks with ceramic fillers.
On the topic of etching, we've also had a question about, can we have our technician pre-etch our restorations before they come to us?
Yes, they can. If the dental technician doesn't feel like working with hydrofluoric acid for any reason, they can also sandblast the restoration. Sandblasting, I would say aluminum oxide, 50 microns, 2 bars of pressure, but be careful, because we try to mill anemics sometimes very, very thin. If you sandblast the outline, you would destroy it. I mean, that's not what we want. So yes, they can etch it already in the lab.
And another question, how does the flexural strength of anemic compare to other glass ceramics, for example?
Again, that's, if you mainly look at the flexural strength, anemic is not a winner. Anemic is only like 140, 160 megapascal, depending on the studies you're doing. And if you compare it to a glass ceramic like lithium disilicate Emax or Suprinity, a zirconia reinforced lithium disilicate, there are 360, even 420 megapascal. So you think, well, they're not so strong. But again, the strength comes from its bonding. From the moment that you bond the material, the flexural strength doesn't matter. If you bond an Emax restoration or an anemic on the enamel, they reach the same strength in the end. It's the flexible materials that will win. It's the brittle materials that break first. But if you cannot guarantee me a good bonding, because you prepped so much, there is no more enamel left, because it's difficult to keep it dry, because there's too much blood and so on, or you say, I'm not going to follow bonding protocol for any reason whatsoever, only then flexural strength is important. So again, flexural strength, we're only going to look at if we have no other alternative. Because if you go for flexural strength, you're gonna lose your flexibility. You will have to prep more. And these are often things we don't want to do anymore. So don't just only look at flexural strength. That's not the most important thing nowadays.
So if we go back to the slide in front of us, that was finished off with essentially direct composite veneers, is that correct?
Yes, indeed.
In a perfect world where you had every chance to do every little trick you wanted, you were saying you probably would have liked to have done, ceramic veneers, is that correct?
Yes.
Okay.
That would be the perfect goal. But again, in this case we couldn't, because we still can, but this patient didn't have any more money, any more budgets. So we just said, let's do it in composite first, but I can still do veneers in like 2 or 3 years if she still wants to. I mean, anemic doesn't discolor. Anemic doesn't change quality throughout the years. So it remains the same strength, the same flexibility. I can still prep and make a small feldspar ceramic or a glass ceramic veneer on top. Yeah.
Great. So can enamic be used in, say, for example, implant crowns?
Yeah, I actually have also a nice case here, because if you make a ceramic restoration and you only replace enamel, then there's not an issue because there still is your dentin that works like a natural shock breaker. But if you do an implant, yeah, then all your flexibility is gone. So all the forces are carried by your brittle ceramic or your rigid implant. So we need a flexible material not only to reproduce the properties of your lost enamel, but also the properties of your lost dentin. We have some good clinical results already. In the study that you see here, you actually see that over 4 years we have a survival rates like over 98%.
It is impressive.
The reason why I actually lost that 1.3% is actually because there we failed the right bonding protocol. So if we actually did the right bonding protocol, we never had any loss.
And those crowns, were they screw retained or cement retained?
In this case, we talk about all screw retained restorations. If you can cement them also, that's not an issue, because more and more we try to go to these screw retained restorations. The good thing here again is that on an implant, you see here on the front picture, that we want a material that's flexible, that can cope with that occlusal loads. We know that if you do ceramic restoration on implants, we have much more chipping, much more fracture than we had ever before. A flexible material will absorb those forces again, and that's great. You can say, for example, well, I'm not going to use your anemic, your hybrid, so I'm just going to put zirconia on top of it. Zirconia is so strong, patient can bite however he wants, I'm never going to break the zirconia. And again, the study you see here is that zirconia doesn't absorb any forces. If a patient bites, then all the forces are carried by, not the restoration, but the implants. If you have a decent occlusion, with some decent canine guidance, and your forces are nicely axial on the implant, maybe it can deal with it. But if you lose your canine guidance, and all the lateral movements are carried by your posterior, where you have your implants, then you have horizontal forces pushing towards your implants. And all the forces are carried by that implant, not by the restoration. Your restoration will survive, but the chances that you lose your implant become dramatically higher.
Very high. So from a perspective of patient satisfaction, something I find and have to warn patients about who are considering implants is that implants will feel different from a natural tooth in chewing because everything's so solid. Do you anecdotally find that patients are more accepting of just the sensation of an implant that's restored with enamic? Or is that something that's yet to be studied?
No, we have patient testimonials. I mean, I have to judge it myself once I will have my anemic restorations, but ceramic always feels hard, feels brittle. I can't imagine how hard zirconia must feel in the patient's mouth, especially if you don't have your dentin anymore, if you don't have your natural shock breaker. By having a softer material, by having material that's a bit more flexible, it would feel also much more natural. Patients actually say that it actually feels more natural dentition.
We have a question about what the material is like under light in terms of, well, the person who's asking the question has a specific interest in translucency of the material.
It's a shame I don't have that slide, because I have an awesome slide where it actually shows all those different light sources compared to other materials. Anemic is a translucent material. You can compare its translucency to any type of ceramic. You can compare it like an HD lithium disilicate, you can compare it to a traditional layered ceramic. That's not a problem. Again, the thicker I mill it, that's what we want to avoid, the less translucent it becomes because you have more polymer. The thinner you mill it, that's where we go for, the more translucent it becomes. The thing is, translucency is not the most important thing. Again, that's something that we make us believe, oh, translucency is so important. Remember, if you have a titanium abutment underneath and your restoration is too translucent, it will shine through. So translucency can be a boomerang that comes back into our face. Translucency is not the most important thing. Remember, most people, when they do a lithium disilicate, they never choose HD because it looks nice onto the table. You have a model like this, it looks nice, But once it goes in the mouth, people say, "Oh, it's kind of grey." So they always go for a lower translucent material, so at least they have some color appearing. Aesthetics, like you describe it, translucency, is only the reflection of light. You know that from in the old days, from physics, biology. You see, it's only how light is reflected is how we see color. Here on the table, there is enough light. Everything looks nice. If you bond the crown in the back of the mouth and there is no light, if there is no reflection of light, how can color exist? If you make a material that's too translucent and all the light shines through it and nothing comes back, it might look awesome here, it looks opaque into the mouth. And that's why these lithium disilicates, nobody takes a high translucent anymore, maybe for nice veneers, but never in the back, because all the light shines through and it looks grey. What you want to have is, like every single material needs, is fluorescence. Dentin is fluorescent, enamel is not. Fluorescence means that that little bit of light that you have in the back of the mouth is absorbed and diffused. That even a translucent restoration doesn't turn greyish because there is a reflection of light. And that's what people want to have. Glass ceramics are very low in fluorescence. That's why actually they needed to be layered by the lab in order to get its best results. A hybrid ceramic may not look as nice on the model compared to a traditional ceramic, especially if you make them really thick. But in the mouth, often they look better. They adjust itself, they take over the color of the tooth underneath to its translucency, and they look vital because of its fluorescence. So don't underestimate a hybrid ceramic compared to any traditional. Try them out in the mouth, see how they work there. Don't judge a material onto the model. That's too easy.
On that note of trying them out in the mouth, you've mentioned sort of bonding protocols and how important they are. Can you talk us through, the ideal bonding protocol for the enamic material? Sorry, there's more implant material?
Well, I can actually show you a quick final case here for the implants. Here you actually see 2 implant restorations where we did it in a chair-side concept. So what we actually did is we put on the scan posts, scanned it directly into the clinic. So there is no reason to make any kind of model. We design them over the computer. They mill actually very quickly. An enamic like this would mill you in 15 minutes.
Compared with, say, a lithium disilicate block, how often would we expect that to take?
Well, it depends, of course, what kind of milling machine you're using. But let's say that I can mill an inlay in enamic in 4 minutes and 40 seconds, wow, where it would easily take me a glass ceramic 10 to 12 minutes. If you take, of course, a screw-retained implant block, where you have to mill all the block to get to that core, then I can easily go for, let's say, enamic in 10 minutes, where lithium disilicate can easily go 20 minutes to half an hour. So it mills razor quick, very precise, even if you mill it very quick. And in a case like this, chair-side concept, we just scanned, milled everything over the computer, polished by hand. Just polish those things. They polish incredibly easily. I mean, yes, you can stain and glaze all you want, but what's the point? Just polish them nicely, bond them in, and you have a great result. Beautiful. Now your question regarding bonding protocol, like I said, you need to bond on enamel. That's the best thing. The more enamel you have, the better it is. So if you say, I want a cement, old school, glasionomer zinc phosphate, I pronounced that correctly in English?
You did, that was perfect.
These materials can't work. I mean, only by bonding you increase the strength of your material. If you bond well, flexural strength does not matter. But if you cement, then you need to use stronger materials. In my opinion, there's only two materials that you can cement. That's metal, because it's strong and flexible, and zirconium dioxide. But any type of glass ceramic, even a glass ceramic, even if the manual tells you, the manufacturer tells you can, don't take any chances. Even 420 megapascal is not enough. Remember Procera? It was 550. Everybody went to zirconia because they felt that it was too weak. So 440 is not much. If you use a ceramic, whether it's a glass ceramic, a feldspar ceramic, or a hybrid, you want the bond. The more enamel you have to bond onto, stronger it gets. If you want to use a self-etch, you can. But remember, self-etch bonds quite well on dentin, but not so good on enamel. So if you use a self-etch, only on full crowns, not on partial restorations.
It's good to know.
You want to do a partial restoration, you do it as you always did with your veneers, etch, silane, bond. I mean, I'm gonna be honest, I'm a dental technician, I'm not a dentist. You know these protocols better than anybody. But where we focus on here is again that we etch the restoration with hydrofluoric acids for 60 seconds, 5%. If you use the 9.8%, of course it's going to be a different time. Since I have not much experience with it, I'll just say follow the manual from the manufacturer. That would be the safest bet. Again, after etching, rinse, dry, silane. Again, silane 1 component, 2 component silane, you can choose. How long does it take? Manufacturer. Vita doesn't have its own bonding kit. We just recommend whether you use Panavia, whether you use Nexus 3 from Care, whether you use one cold and weld. That's whatever you're used of working with. Just use the same bonding protocol you use on your traditional ceramic veneers, and then you're safe. So
beautiful.
Oh, if you do it on an implant, for example, that's something else, because if you, for example, have a titanium interface where you work on, of course, a titanium interface cannot be etched. So here's the bonding protocol is a little bit different. Here you would sandblast the titanium interface just with aluminum oxide, create a mechanical retention, and you will use a silane, for example, Monobond Plus, to create a chemical bond. The ceramic itself is etched again, is silaned again, like we discussed before, and then with our single Ivoclar hybrid abutment cement, then you can just, it's dual core, just bond them both together. If you do this protocol correctly, even though we bond on a titanium interface, we still have an awesome strength and an awesome quality. You saw it in the study that we did before.
Really high survival.
But it is important that you follow that bonding protocol, so you have to pay attention to it.
Okay. In terms of, we've had a question about sort of which CAD/CAM systems are suited to Enamic. Is Enamic able to be used across various platforms? Or?
It can. I don't know any machine that doesn't mill Enamic nowadays, or it must be some strange third world country system. But no, every common system on the market, whether you use a chairside system like Sirona or Roland, whether you use a lab machine like Imezaik or Amann-Girrbach, whether you use huge industrial machines like a Sauer, it all works. Again, because even if you don't have the template, even if it's not in your list Enamic, like in the beginning days of CEREC, we just choose a traditional ceramic and it mills it even without any problems. So you could actually cheat your way around it if you wouldn't have Enamic in your material list.
And I believe the Enamic isn't so taxing on the CAD/CAM burrs, like the burrs last longer.
Again, it depends a bit on the milling strategy of your machine, but we've done studies when it came to CEREC, and to give you an idea, with one set of burrs, and these burrs are not cheap, we could back then mill about 20-25 lithium disilicate crowns, because that was the hardest we could find back then. If you would take a feldspar material, we could mill like 40 to 50. In Enamic, even if we speed milled, like extremely fast, we could still mill about 150, 140 crowns before we had to change the burrs. So the way it was not only good for your antagonist or for the material, but it's also good for your machine. Again, if you have to change every 20 crowns your burrs, and it costs like what, $100 for a set?
It's all going to add up pretty quickly.
It all makes restoration much more expensive.
Yes. We've had a question, can Enamic be used to make a post and core?
I actually don't know if it in this, I don't think I have it in this presentation, but yes, you can. If you want, we have some great, there is now a magazine called Dental Visionist on the market, which is written by dentists for dentists, which you can find anywhere on the internet. They have a great article where they show you how to make a post in Enamic. Let's say in the old days in the lab, what we did was take a zirconia post and then just wax it up, press it in ceramic. Now I just mill it in Enamic. The flexibility will make sure the post doesn't break. and you have a tooth-colored, flexible, dentin-like material underneath. And then you can still choose to put a ceramic crown on top of it. That is actually the best. Like in nature, ceramic on the outside, flexible dentin, polymer on the inside. That's how it actually should be. I'm looking forward to studies on that, how that it behaves throughout the years.
It'll be a fun space to watch. We have a viewer's asking for clarification. So what you were saying is if something is flexible, if a material is flexible, will it not debond as easily?
Yeah, that's a good question. The reason why these indirect composites suffered massive debonding was on the one side, of course, the difficulty in etching. You couldn't etch, you have to micro sandblast, but also because if you put them on the list, you will see that your composites are even more flexible than a hybrid ceramic. They have where anemics like 30 gigapascal, these materials were like 20 to 10 gigapascal, so they were even more flexible. I mean, a material, if you put too much force on it and it's flexible, it bends. Combine that with a low bonding strength, yes, and they debond. So the question is, why does anemic not debond like an indirect composite? Is because they're a little bit more rigid, so they're flexible enough to absorb forces, but not too flexible to debond, and because we could etch them, so we have a much more better mechanical bond.
Now, if we were to construct a post-core from anemic, I'm a big believer, well, I use a lot of glass ionomer materials, but I glean from what you're saying that I should only be bonding that with a resin cement, is that correct?
Yeah, that again, the strength of anemic comes from that bonding. Always the same thing, if you have doubts whether a material is strong enough, look at the flexural strength. If it's low, you need to focus on that bonding. That is priority. If the flexural strength is really high, so glass ceramics or even zirconium for that matter, then your bonding protocol is less of an issue. So the question in material choice is always, how well can you bond? How much are you going to prep? Because by prepping more, your enamel is gone and your bonding quality goes down. By prepping less, you have more enamel, your bonding quality goes up. So these are two important questions. How much are you going or willing to prep? How much tooth structure are you willing to take away? And how does it affect your bonding? If the bonding fails, if it's limited, go for flexural strength. Even if that means sacrificing precision, even if that means to do a decent crown prep, even if that means to make more time to make them, and it's like it is. But if you have a decent bonding protocol, go for anemic. The fact that it's flexible, the fact that you can repair it, the fact that it can be used in even the most, dangerous situation. We have to be careful, of course, what we say.
No, I understand.
But even patients like myself, we finally have a material that we can treat these patients and don't worry about every single second that he's on the phone saying, well, it broke again. I know how much fun it is to wake up in the morning and breaking a veneer because you just put for one time too much force on it. And even imagine you break in a lithium disilicate. As a dentist, you must know how much fun it is to grind that baby
drill it off
out
and start again.
and start again. And every single time you grill it off again, you're going to take a little bit of enamel with you. So these are things you want to avoid. You want, as a dentist, to have, how do you say, peace of mind?
Yes.
So that you can say, okay, this is not ideal, but I've treated the patient without taking any material away,
Any tooth structure
in a
away.
flexible material, and I know that if something goes wrong, and those chances are slim, that at least I can repair it myself. I don't have to start all over, annoy my laboratory, because these are discussions you don't want to have.
Oh, annoy the patient as well.
You know what the patient's saying, okay, you have to come back a second, and can you guarantee that it's going to work next time? No. So confidence, like I have confidence from the patients, your time, new appointments, the discussion with the lab, who's going to pay for the crown. These are things that gives you headaches or a heart attack, for that matter. So now, one peace of mind, even in difficult situations.
Speaking of difficult situations, I think you have some slides of some parafunction patients. Is that correct?
Yeah. What I always like to end with is a patient like this. Again, these are examples I use from Dentists we know very well. Again, this is not my own work. I have to present, so I'll always put the picture of the dentist next to it. This is their work. The case you see here is an Armenian, I think Armenian or Turkish truck driver in Holland. This person walks into the clinic of dentist Sjoerd and he says, "Doctor, I have splitting headaches for over 10 years, but really extreme splitting headaches. And I've went to every single dentist in Holland. Nobody can help me. I mean, I've lost my job, I'm depressive, and I'm pretty sure I'm about to lose my wife. Can you help me?" You mean, look at this photo. This is the kind of patient that has no self-esteem. He's a wreck. He doesn't look in your eyes anymore. He doesn't smile. And you think, well, if no single dentist in Holland, and dentistry in Holland is quite a good level, if they can't help him, how should Sjoerd can help? But let's just take a look at the patient and we'll see what we can do here. And then you look at the occlusion, you think, oh my God, I mean, no wonder you have splitting headaches. If you have one single contact points on the premolar, then, my God. So let's just try to find a decent occlusion first. Let's just try to lift that occlusion by any means necessary. You know the tricks, the length of the incisor towards your lower lip. You can determine the position of the canines, but the length of every single trick in the book is good to determine the perfect plane of occlusion. And let's just stabilize the patient there and see if it helps. Because if it doesn't help, what's the point in making final restorations? Most likely it's not going to help because 10 years and counting and nobody's been able to help them. So by all the tests we've done, we decided that the bite need to be lifted at 9 millimeters.
Oh.
So that's massive, 9 millimeters. We made a temporary PMMA splint and we just fitted it in. We'll see if it works. If not, at least we've tried. Patient,
is that the splint there?
That's the splint. Okay. It looks really funny. But again, the patient walked home. He walked home like this. And the patient called the same evening, crying in tears, that for the first time in 10 years, he had no more headaches. So it actually meant that we were on a good way here. This was the solution. But you know that you can't just take it out and make final restoration. This is 9 millimeters that we talk about. So we said to the patient, we're gonna let you walk around for this like a year and a half before we stabilize the entire occlusion, and then we'll do final restorations. The patient said, no, just bond it in like it is now, I'm happy. Screw it, we're gonna move it like this. We said, no, I mean, honestly, I understand you're happy, but this is not the way we do business around here. So after a year and a half, when the patient came back, the headache stayed away and so on, we want to reproduce the exact situation. Why produce anything else?
Exactly.
We were happy. So what we do here is a double scan. We use a different software. This is not done with the CEREC. We use a different software just to show you that you can do it with any kind of system. We scan before, without, and with the split. And we just fill up every crown and we lengthen them completely. So instead of one massive block or one massive bridge, we have like every single restoration. Why was it so important to use anemic here? We have enough room, we can do zirconia or ceramic or whatsoever, but in a dangerous occlusion like this, I don't take any chances. I don't want my ceramic to chip. I want the material again that is a natural flexural shock breaker and that can be repaired if things go wrong. But also much more important, we don't prep. So our outlines finish to 0. I don't know any ceramic that can be milled to 0, even if you would press it. So that's why it was so important for us to use a hybrid ceramic, because we can finish those outlines to nothing, that you don't feel any limit. Of course, by making them so thick, the aesthetics was not perfect. But honestly, this patient did not care one bit.
If he was comfortable.
He was comfortable with the split. So he will be comfortable with this as well. Of course, we do our best to make it as nice as possible by staining and glazing. We can even do a cutback if we want and build it up with direct composite. But then we're struggling with the financial part. Don't forget, this is an unemployed truck driver. I mean, he is not rich. So we try to do everything we can, and you see here by reproducing a bit of the root, by with some blue texture, try to create some translucency, everything what we can. but it's function over aesthetics in this case. This is really rehabilitate occlusion. So this is how it looked like, and you can say, I've seen nicer. Yes, but that's not our goal here.
Compared with the starting point, that's remarkable.
And again, what's aesthetic? If the patient is happy, who are we to complain? You just don't want to see that patient standing back in half a year with broken restoration and crying again.
Exactly.
So now you have to see in this final slide, this is how the patient came in. Again, depressive, not looking in your eyes, not smiling. And from the moment we bond them in, he smiles, he looks at you, he's confident, he starts flirting with your nurses instantly. And this guy, for the first time, he's confident again. I think 3 months later he called that he had a job again and he was really looking forward to life again. This is the type of patients we want to treat. It's not a single crown, a simple inlay. No, this is complete occlusal rehabilitation. Combine it with modern dentistry like implants, what we do more and more, or like minimal invasive dentistry, what we seek more and more. Then you will see that flexible materials, like a hybrid, is actually the material of the future. And that brittle ceramics, actually where you still need to do full crown preps and so on, are falling, not obsolete, but falling more and more behind. The success of direct composite proves it, that we want to go more and more to these type of restorations. From single crowns to non-prep veneers to the most complex cases ever.
We're almost out of time, but you mentioned staining and glazing in what you were saying a moment ago. What options are available to us on that front for Inamic?
Well, there are multiple options. Again, it's what we want to do. If it's only to rehabilitate occlusion, I would just say polish them. You mill them, they polish really easy, so flex, and in like 2 minutes these things are polished to a nice glaze. And polish is always there. Even throughout the years, your shine will remain. If you say, well, I need to stain and glaze a little bit, you have light curing stains. These light curing stains are quite okay, they have a good aesthetic result and they have the same quality as your ceramic stains because you will etch the outside of your restoration or sandblast it first to get a good mechanical connection.
And that's etched with hydrofluoric?
Yeah, the same protocol, hydrofluoric acid 5%, 60 seconds, and then use a silane as a monobond plus as a chemical bond. Then I can assure you these stains will remain for years and years to come. But, and that's a big but I'm having personally, light curing stains do contain monomer. Monomer is not the healthiest thing to use for yourself as for the patient. So keep the staining and glazing to a minimal. Use it occlusally when you want to see those effects, but stay away from soft tissue, especially if you make one. I mean, we want to see long-term studies first, but a personal approach, I prefer polishing. One last step is, mainly for anterior, if you say, well, the aesthetics I could do nicer. You could do a small incisal cutback, or the lab can do a small incisal cutback, finishes the crown, and you can, with some direct composite, with enamel, just give it a bit more translucency. If you're the type of dentist that loves playing with direct composite and is willing to put in extra time, or you can ask the lab to do it in indirect composites, you can go very, very far. But remember, a hybrid ceramic is more about its functional properties, not so much about aesthetics. We have enough alternatives for aesthetics, glass ceramics, even a nice metal ceramic restoration can look awesome. But we need it for its flexibility. We need it for that minimal invasive approach. So don't focus too much on your aesthetic approach, even though you have any combination, every possibility you want. The last thing you cannot do is put it in a ceramic furnace and fire it. If you put polymer at like 920 degrees, your ceramic is still there. You can still try to bond it in, but it's like Swiss cheese. So I wouldn't go for it.
That's all good to know. Look, sadly we're out of time. Thanks again, Tom, for joining us. And thanks again to you, our audience, for joining us as well. Henry Schein Hallis have a shiny new YouTube channel where you'll find all previous episodes of ScheinTV as well as other videos. So to stay up to date as new content gets added to the library, head over to YouTube, search for Henry Schein Hallis and hit subscribe. I hope you've enjoyed tonight's event and remind you that if you haven't already done so, you can click the button below the video to register for your CPD certificate. Dentists in New Zealand can register for their CPD certificate by emailing Henry Schein. Thanks again and see you soon. on ScheinTV.